Okay, so good morning, everybody. It's 11. I don't know if in the US it qualifies as morning. In Italy, it's morning. Somebody may think that I am an organizer of the conference, but I am not. I am organizer of the program, and by KITP rules, I am not an organizer of the conference. So I'm not violating any common wisdom by being a speaker here. Okay, so having made the necessary disclaimers, so I would like to present you some work that I have been doing. It's a route, so there are already some papers outside, but I would say the big goal that I hope it comes evident from the talk is still a bit far from being fully realized, and I hope you can tell me what's your opinion, or if you have made some work on this or anything. Okay, so basically, well, during the program in the last few weeks, we had a lot of talks which summarize a little bit the status of long-range interacting system, especially in the quantum regime, but for the sake of the people that are in the audience that were not at the program, which you can still listen to some of the talks online, let me recapitulate. So when I talk about long-range interaction, and I think most of the community that we met at the program does agree on this, we talk about systems in which the microscopic components interact via two-body potential, which is a power law of the distance between those components. And the power law is somehow unspecified, and as a function of this power law, different situations may apply. Okay, here I did a schematics, and basically, okay, you know there are a lot of, like power law interactions are somehow natural, in the sense gravitational, it's 1/r, also Coulomb. But the reason why we are now interested to this generic power law that may seem a little bit artificial is that we have tons of quantum simulators that realize different regimes. We have, for example, Rydberg quantum simulator, which normally realize dipolar interaction, can be 1/r to the 6 or 1/r to the 3, depending on the orientation. But they can also realize complex geometries nowadays, and it will be crucial for the rest of the talk. Then we have trapped ion systems in which you can really tune your decay exponent between 0 and 3, basically in 1 or 2 dimensions. So you can lie in this line. And then you have, well, you can also go beyond this. And then you have cavity systems, so systems in which you have matter coupled to the standing wave of an optical cavity, in which the photons of the cavity, which has a flat k equal to 0 momentum, basically can mediate interactions which are all-to-all. So basically, there are these different regimes, and so if the system is ferromagnetic, so if it tends to build some kind of homogeneous order parameters, normally you have different regimes that occur if the alpha is larger than the dimension p plus 2, or inside this regime that we call weak long range, and also when alpha is smaller than the dimension, for obvious reason, this potential is not, the mean field energy is diverging, and you have to do some tricks to renormalize it. So you see there are different interesting situations. The focus of my talk will be mainly in this region, but we can also talk about the strong long range case if you're interested. Okay, so there are, as we have seen also from the previous talk, there are a lot of interesting phenomena that arise due to long-range interaction. So we are interested on them because they come by in this kind of experiments, and we want to study them more because we think that they are a good resource of novel phenomena that we can use in quantum technology. So, for example, there is, of course, the fast signal spreading. We have seen before a talk on Lieb-Robinson bound, and now power law interactions modify the Lieb-Robinson bound. There are novel phases like time crystals. If you have long-range interactions that are strong enough, you can witness like these coherent phases of matter. And also we have this very often system with long-range interaction, if alpha is small enough, lead to ergodicity breaking. And so all of these, I would say, are just a glimpse of the different kind of phenomena that can be realized in long-range interacting systems that you normally do not witness in local systems. So this long-range interaction, at least in my opinion, they represent a new world in which you have a lot of, which has a at the center somehow of something that's already known. No? We know a lot about quantum and classical systems with local and finite range interactions. We know kind of a lot about classical systems with long range interactions. So there are people in the audience that have worked on this, and there have been reviews talking about this. And also, I would say the case of flat interaction, so alpha equal to 0, it has been for a long time, the so-called mean field models. There have been for a long time an instrument of theoretical physics that were like exploited, so we know a lot also about them. And the present community is focusing in understanding what happens when alpha is somehow intermediate and the system is still quantum. And in here we find all of the phenomena that we have been talking about during the conference and the program, which still we don't understand completely. And the reason why we don't understand completely, or part of the reason, is that our standard techniques to understand these systems are not so good. In the sense that, okay, for classical systems, traditionally we have classical Monte Carlo and large deviations. Well, for quantum system, what we use are mean field methods, but these mean field methods only work exactly for the flat interaction case. And we have numerical techniques, of course, to understand, but these numerical techniques have been normally tailored to local systems. So quantum Monte Carlo, DMRG, tensor networks. I'm not saying that they cannot work with long-range interactions, but for sure their performance it's worse. It's difficult to go to large enough systems that we can understand the thermodynamic limits. So from this, I think I wanted just to convince you that we need some new tools. And what I've tried to do in the last few years is to imagine what a new tool can be. And this tool, I mean, it's thought to overcome the fact that long-range interactions are so connected that numerical simulations are kind of hindered by this connectivity. Now, you are not talking anymore of triangular or sparse matrices, you are talking about full matrices. Whenever you draw, imagine you want to diagonalize even a stupid system that you can diagonalize, like a free fermionic chain. If it has long-range interaction, this is a full matrix. As soon as it's translational invariance, is no problem. You can use momentum basis. But as soon as you lose translational invariance, this is a mess. It's a full matrix. It's numerically tough. So this is what I was trying to convince you. Okay, so now, in order to convince you that this problem of the all-to-all couplings can be overcome in simple means, I have to do a step back, and I want to take a model as an example. Okay, well, this is the model that everybody likes to talk about, I think. Probably 99% of the people in the audience have worked in this model at some value of alpha. So the model is the transverse chain, is the transverse field Ising model on a one-dimensional chain. We have the usual ferromagnetic, the interaction is ferromagnetic, so then we can talk about the antiferromagnetic if you want, but let me take the ferromagnetic, it's easier for me. And the only little tweak that I'm going to add to the standard textbook example is the same tweak that many of you have used. I introduce a ferromagnetic coupling, which decays as a power law. And as I said before, depending on the value of the power law, I may have to introduce a coefficient that scales as the system size in order to restore energy extensivity, but okay, this is not crucial. The interesting part is that for any value of alpha, so from 0 to infinity, I have a quantum critical point in this system. So it exists a value of h such that when j is larger than h, I have ferromagnetic order, and when j is smaller than h, I have paramagnetic state with exponentially decaying correlation. So this is true for all values of alpha. Okay. Now, how can I understand the feature of this critical point, no? Okay, in the alpha infinite case, you can solve it exactly. Everybody knows the critical exponent and everything. If alpha is not infinite, we can do something else, and let me do something very simple, a little bit in the spirit of what Leo has done yesterday with the Sine-Gordon model. I will do very simple mapping, and which is, of course, approximate, and translate my spins into bosons. Okay? Okay, you say, if it's as long as if it's low energy, this shouldn't be so rough. Well, it turns out to be rough, but let's do it nonetheless. So I take any of the spin and I at the spin operators and then translate into boson operator, and I get a bosonic Hamiltonian. And so it happens what we said yesterday, what we have seen yesterday in the talks. Basically, the connectivity of the, now I can diagonalize my Hamiltonian exactly, it's quadratic, but when I take the Fourier transform is not the usual cosine, but is a sum of infinitely many cosines. And if I sum infinitely many cosines, what is interesting is that at low energy, I can get a non-analyticity. Do you want to make a question, Leo?
Yeah, just comment. There should be non-conserving terms as well.
Yeah, I think if you do it exactly like this, oh, you're right, sorry. Ah, no, I don't need it, So, okay, yes, Leo is saying that there should be non-conserving terms, so that you can have also terms, say, dagger, if you do this kind of transformation. I think in this specific case, if you do this one, they won't, but it depends on the value of j and h, because they can cancel or not. It's not important because it's still quadratic, I can still diagonalize and I can still get non-analytic terms. So if you want to do the calculation exactly, you get a different dispersion relation, but at low energy it will always look like k to the sigma or k to the sigma alpha. So the point, it will be non-analytic. I think this one, it should be like this when they are bosons. Well, okay, well, we can discuss it. No, but the Kitaev is fermions, these are bosons. If you get a minus when you do the commutation and it cancels out, these are bosons, not fermions. So I think for the boson, there is a minus sign that cancels the terms that Leo says, but it doesn't matter. As I said, what's the crucial point? Low energy, it goes like k to the sigma. Okay, this is true. Okay, so you do this thing, and okay, well, normally you don't do this when the system is translational invariant, of course, but let's do it nonetheless. Let's introduce density of states. No, density of states, it counts how many states you have at a certain energy. This is its definition in 1 dimension, in 3 dimension. The generalization is trivial. And so this non-analytic power in the momentum translates in a density of states at low energy, which goes like this, where ds now is 2d over sigma. So ds, if this were a nearest neighbor system, or even a finite range system, this power will be bound to be 2, or anyway integer, and this ds will be the geometric, not geometric, the spatial dimension of the system will be d. But now, due to the long-range interacting nature of the system, we get that the low energy tail of the density of states has get some dressed dimension. I don't know how you want to call it. Sometimes we call it the effective dimension, whatever. And this is the spectral dimension. Okay. So during my career, I worked quite a lot on long-range interacting system. I don't pretend to make a review of all of what I've done, but I have also written 2 reviews, one with Andrea, Stefano, and some other people, and Guido, Tobias, which are all in the audience, and one also with Silvia and Alessio, which is hopefully published soon. And what I noticed that I will say a big portion, for sure the majority, and probably more than 80% of the phenomena we are interested in do not crucially depend on the form of the interaction, but only on this low energy physics. Okay, a system that has this kind of low energy will still violate Lieb-Robinson bound, will still present strange non-thermal phases, prethermal phases, time crystals. So all of the phenomenology which appears in long-range system, or most of the phenomenology we have been discussed, just depends on these modified low energy features. Okay, then I said, okay, I just have to find, well, first of all, let me say that this doesn't come as a big surprise, no, in the sense, the spectral dimension is known to be so is known to control, of course, the vibrational spectrum of random Walker behavior on a certain geometrical structure, but it's also known to control like the phase transition on such geometrical structure. So it's not a surprise that a lot of features that we observe crucially depend on this quantity. If you go and ask to people that work on graph theory, on complex network, they will say, okay, yes, that's known. Like universality, low energy physics only depends on the spectral dimension. It's a known fact. So the question is, can we find a system which has a lower connectivity than the long-range interacting system we used to, but it has the same or very similar spectral properties? Okay, but the answer is kind of simple. So we take a regular lattice in one dimension with nearest neighbor coupling. And now for the moment, I ask you to make a little bit of an abstraction. Don't think about the Ising anymore. Think only in geometric terms. So this is an ensemble of links and nodes. Okay. I take this, so now I represent my nearest neighbor system, just a chain, periodic boundary condition, sides, and the links represent my interaction of the model that I want to put on it. But I don't put any model. This is just a graphical representation of a coupling matrix. I start with all nearest neighbor links turned on, and then I decorate it by adding additional bonds at random. The bonds all have the same strength. This is crucial. It's a matrix made of 1 and zeros, or if you prefer, of j and zeros. There is no, so long-range interaction will be colored. Each entry in the coupling matrix will have different values. But in this model that I'm telling you about, the coupling entries are 1s or 0s. It's purely geometric. There is no information. And the links are drawn with a probability that decays as a power law. I put proportional because you may want to put it proportional in certain situation, but let's say it's equal. So this, when it's equal, it's perfectly what I'm describing, no? If the distance is 1, it's always on. I already said that. The longer the link, the lower the probability for him to exist. If I repeat this n squared times, but there are ways to generate this graph in a time that's n log n, I get a structure which has a linear number of bonds. Actually, I can also reduce the number of bonds. The number of bonds is something that I can also control, but this, if you don't have a question about this, I will not say it. Let me say for the moment that the number of bonds is linear as long as alpha is larger than the dimension. So this matrix is sparse. Okay? This matrix is sparse. It's made just of 1 and zeros, but it has the same or very similar spectral dimension to a fully connected long-range interactions. And this doesn't kind of come as a surprise because, you know, if you take this guy and you average over his probability distribution, you get the longer. So if you look at it as a random matrix, you average it, the average of the matrix is long-range couplings. But when you average over the spectrum in one dimension, you get these numbers that you see here. Okay? So the dashed line would be the spectral dimension of long-range interaction in 1D. It's 2 over sigma. And when you average over the spectrum, you get something like this. So the disorder does influence the things, but not so much. Okay? Okay. For me, this is very interesting because this action of disorder on this spectral dimension, it looks like it has something to do with the universality of the Ising model or of ON models in general. Because you see, the deviation starts around d equal 4, which is the upper critical dimension of the Ising, and it terminates in d equal 1, which is where the Ising model is expected not to do any transition. Well, it's expected, it's proven not to be any to have any transition. So even if you plot this deviation, it looks like an anomalous dimension of a ON model, but on this I don't want to go too much. So, okay, when I first saw this, okay, I was already a little bit annoyed. I said, okay, even this, I thought it was super simple. I thought that this disorder was completely irrelevant. It already shifts my spectral dimension of something that is anyway of order like 1/2 in here. So I said, okay, let's do something a bit simple. Let's change it a bit, the rule of the game, and let's do the 2-dimensional version of what I said. Okay? Exactly the same as I said in 1 dimension, I redo in 2 dimension. I dress my lattice, same rules apply. This is an intuition by Giorgio Parisi that in 2 dimension the disorder would be irrelevant, and it appears to be true. I am completely astonished by this because I thought that the relevance of disorder would be controlled by the spectral dimension, not by the geometric dimension, but for some reason it works. And you see this, it's in almost perfect agreement with the real, so with the expectation from the midfield model This deviation, I think, is not real. It's only finite size correction, because close to sigma equal to 2, you expect to have logarithmic correction. So it's very hard to make the fit there. So I think this deviation is a real one. It's stable. We tried it. You see many different methods, different Monte Carlo simulation. This deviation is consistent. This one, I think, is just a logarithm. If you go to enormous sizes, you will wash it away. And on this kind of network, okay, sorry, it's already on the archive, this paper. But if you try to take on this network a model of critical phenomena, and in this case we did a classical model because we wanted just to make a proof of principle, you can see that the critical exponents, and this is the critical exponent nu that we talked about a bit yesterday, the correlation line critical exponent of the self-avoiding random walk. So self-avoiding random walk is a non-interacting model. It can be written as a quadratic field theory, but self-avoiding random walk is a 5 to the 4 theory in some crazy limit. And when you do these critical exponents numerically, you see that the one of the sparse model and the one of the fully connected model, they do agree almost perfectly. There is a little bit of a mismatch, but this is in 4 dimensions. Again, in 4 dimensions, we know there are logarithmic corrections. So these mismatches in these two plots are mostly due to finite size effect. But in here, you see, we have almost a perfect match. Of course. Yeah, you're right.
You say fully connected long range, but then you also plot it as a function of alpha. Isn't alpha always 0 for fully connected long range? Or is this a different
No, sorry.
This is not that alpha? This is a different alpha?
Yes, you are very right. This was...
Sorry.
No, it's... let me... you're right.
Sure.
Just a moment. 3... Yes, this axis... No, this should be sigma, I'm sorry. So this is alpha minus z. Sorry, yeah, you're perfectly right. Because it diverges when you approach 0, so it's obviously sigma. Very sorry. Okay, Archana is completely right. This is not alpha, but alpha minus the dimension of the system, which in this case is 2. So this axis will be alpha minus 2, and I apologize if it's misleading. Okay. So, okay, this matches, so we're pretty happy about it. And so what I tried to convince you during this talk, and what will be my goal of the near future, is to try to convince you that not only fully connected long-range interactions are interesting, but that most of their phenomenology can be reproduced in a network, which is, in my opinion, nearest neighbor, because if you look at these matrices, are only 1 and 0s. So there is no concept of long distances in it, no? You build it by embedding it in a metric, if you allow me this mathematical jargon. But when you take it out of it, this is just a coupling matrix made of 1 and 0. I think it would be perfect to be realized in a Rydberg atom quantum simulator. No? Rydberg atom can do all sorts of complex geometry. This is a geometry that one can do. This geometry is much simpler to be simulated numerically. The matrices are sparse. You can say there is disorder, but this disorder is unfrustrated. It doesn't produce bounce set. It doesn't produce glass behavior. It's unfrustrated. All the links have the same value. So it has the same transport properties. It's enough to have these few long-range links to still give you the transport properties that we all like and cherish. Fast entanglement, fast information spreading. And so this is basically erase it. Please. Ah, yes, the microphone. Okay. No, it's at the end. Here.
What is the average coordination number for your?
Okay, so the average coordination number. So basically, the average coordination number is where is it? Okay, because I put a proportional. So the average coordination number for alpha larger than the dimension is the zeta, the Riemann zeta function of alpha minus the dimension. But this you can change, because you can change the coefficient that's in here, and the coefficient that's in here control the average coordination number. And in this paper, we have shown that as long as this coefficient is above a certain critical value, which is just a percolation problem. Now, you need this coefficient to be large enough for the model to make a giant cluster. So C, the coefficient equal to 1 obviously gives a giant cluster by definition. All the nearest neighbor links are connected. But if you pick a smaller C, there are a lot of values for which you still got a giant cluster because it's a percolation problem. In the thermodynamic limit, it will always percolate. So as long as C is above that number, then you will have that the spectral dimension is the same. So you can reduce your coordination number, you can control it by C. I think you can get it down basically to something between 2 and 3. Because a one-dimensional lattice to be fully connected needs to have at least 2 neighbors, and so I think it's between 2 and 3. For the 2-dimensional, it will be something around 4 to get a fully connected. So this is possible. Okay. Okay, so this I said. Okay, I'm not saying, in some sense, okay, I want to sell this as an analog model. So it's a model that's in a complex geometry that we can realize nowadays, a lot of complex geometry in Rydberg quantum simulator. So I think this would be a path to explore the physics of this model. But I don't want to say that this model is perfectly identical. You have already seen me reserve some surprises. In one dimension, you see some mismatches which I still do not understand. Maybe somebody does understand it, but I don't. And also in the results that I've shown you before, there is something interesting because, okay, here I compare with the expected values for the fully connected long-range interactions. And these values are expected to be not exact, but very, very good because this model has some supersymmetry, some hidden supersymmetry that makes it almost solvable, let's say. But now the question is that, okay, if the results do depend only on the spectral dimension, this will mean that I can also compare the results of the long range with the results of a short range at the same spectral dimension, the results of the nearest neighbor. And this is what I report in this plot. You see, these are the MC simulation in the regular lattice for the same model. And this is a problem that we have investigated a lot with Andrea. And as we also state in our paper, there is a deviation. So, and what's my point is that I cannot tell you if the model that I have in mind is in the same universality of the long range or of the nearest neighbor in an effective fractional dimension. I know the two things not to be identical. I know it. In principle, I do think that the model with all the couplings the same value, it looks more close to a nearest neighbor system in a fractional geometry than to a long-range system. The deviation is small, but not just for this model. This deviation is small in general. So we really need a very large size and a big simulation campaign that probably will not. This difference is irrelevant, I think, for quantum system. We don't have numerical nor experimental resolution to see the difference. Maybe with classical system, we will have the numerical resolution to decide if the red point that lies here is closer to the blue circle, but this, in this moment, I don't know. Okay, so basically what I wanted to show you is that the long range is interesting because it manipulates low energy physics. It allows you to enter different regimes of the low energy physics, which is something that you cannot do with any nearest neighbor interaction. This is mathematics. A finite sum of cosines will always be analytic. You need an infinite number of cosines to get some non-analytic behavior in the spectral dimension, in the spectrum. But yet you can get the same or a very similar effect by manipulating the geometry. And this may be easier in some experimental realization that we have. And when we couple this spectrum tunability, these spectral properties that we can manipulate by a knob, with the strong interactions that we have in the Ising model, in the Rydberg chains, I think we will witness a very interesting novel phenomena, and we can maybe also exploit those novel phenomena to make some quantum technological applications. Okay, basically my talk has come to an end, right on time, I would say. I have to acknowledge my collaborators, so Andrea and Stefano. Andrea is here, Stefano will come in a few weeks. I've worked in the first part, and on the part on the non-homogeneous lattices, I worked. Anna is the person that did the numerical simulations, but also Giacomo Gori and Tillman and Federico helped with the many-body and the network theory perspective. I have some funding for this kind of applications, both for the European Union and from the Swiss National Science Foundation. So this is just to say there are some positions open. If you're interested in these themes or in general on long-range quantum many-body theory, drop me an email. Okay, there is no thank you, but thank you.
Thank you, Nicolo, for the great talk. Can you comment a little bit on the ergodicity breaking that you mentioned at the beginning and the return states? So is there sort of...
So basically, okay, this is I would say more... So what I do believe, and many people in the audience know, and it's also written in this paper, that this ergodicity breaking, it derives, or it's so, maybe I cannot say that it derives, but it's strongly connected with the fact that long-range interaction with alpha smaller than the dimension have a quasi-particle spectrum which is discrete. So when you have alpha, this is kind of also intuitive if you want, no? When the model is very connected, like for alpha smaller than the dimension, you go to the thermodynamic limit, but it doesn't look infinitely extended, it looks like a single point. And so the spectrum looks like the one of a confined quantum system, and it means the spectrum remains discrete at low energy. Instead of building a continuum, it remains discrete. This is something that I think people from black holes, quantum information like Maldacena, they know very well, no? When you do a model of a black hole, like the such that Kitaev, at least at low energy there is a gap, which you don't have in standard many-body system. They are gapless, at least at the critical point or in the vicinity of the critical point. And so only with this feature, one is able to build some effective models that show that the entanglement entropy does not grow linearly in long-range system, but it's saturated. Just taking into account that there is a discrete spectrum. This is enough to show that it looks from transport properties point of view, it looks like a single point more than a big system. And I think the same, so as I said, I don't think this, I think it can be said safely. If you do the same procedure with a disordered system, with alpha less than d, you will still get this feature. So you will get that the spectral dimension goes to infinity. This is exactly shown here, no? Or here, what Archana was noticing. When alpha goes to d, so alpha minus d goes to 0, the spectral dimension goes to infinity, it means that the spectrum is developing a gap. And when the spectrum is gapped, it's hard to equilibrate, because you always have modes which have this finite gap, they will not dephase. They will stay there and oscillate. If this in the quadratic approximation, of course, in the if I model my system with quasi-particles, of course I can. But I cannot tell you anything what's happening when you have strong interaction in the middle of the spectrum. So I think Silvia is more expert on me than this. I think that these low energy properties turn out to be, if you look at them in the many-body spectrum, to turn out to be like quantum scarce. So it means that there it depends on the initial conditions, and certain initial condition will have this infinite recurrence time, and certain initial condition will just thermalize. But this, I think, is very open questions.
Well, I will give the word to me for a change. You come after me. So the question is, I mean, this is very cool by replacing your many connections by a few connections. I have a couple of questions. First, is there any proof other than numerical that this works? Second, what happens if you get into frustrated systems? And third, which alpha don't you get an advantage anymore?
Okay, so basically, let me say like this. First of all, there is a fundamental perspective and a model perspective. So if you look at this model, it's obvious that this specific model where alpha is smaller than d, you lose the advantage, because it will start scaling as n squared. But as I was saying, you can modify this. These models exist in network theory, like the Erdos-Shreni, and at low energy, they still look like the fully connected one. And they will have a gap, and the gap will scale in the same way as the fully connected long range. So I think this trick is in principle valid for all alpha, but you may have to, for sure, for alpha smaller than D, you have to introduce a different model with some parameter here that controls the connectivity. So this is the answer to your last question, so I'm going upwards. Then what was the other?
Frustrated systems.
Huh? Frustrated system. When you get to a frustrated system, then it's fun and terrible because there is an interplay between the long range. So the such Devier-Kita is a frustrated system, not because the couplings are fully connected, but they are not just 1 and zeros, they are all the values. As I said, from the low energy perspective, if you look to the spreading of entanglement in the such Devier-Kita, and I asked also this to Maldacena, it looks very close to this. So from the low, at a long time. So when a long time probes low energy. So I would say the low energy properties still will be maintained, but that the frustration will build some continuous portion of the spectrum somewhere, or on the other end, if the alpha is larger than D, we'll build some localized state somewhere in the middle of the spectrum, and it will mess up things, of course. But I would say that the low energy perspective will be maintained. And then there was another one, not what.
Whether you have any proof other than numerical.
But I would say proof in the sense of mathematics, no. There is a mathematical proof that the fractal dimension depends on sigma, and there is a conjecture inequality that the spectral dimension has been larger than the fractal dimension plus 1 or 2, I don't remember. So there are strong mathematical indications. There is the fact that when you average over the graph, which of course is not the same averaging over the spectrum, when you average over the graph, you get exactly the same results. From a physics point of view, I think this is bulletproof.
Okay, thank you.
Nicolo, I have a question. When you were telling us about that's the correct slide for that, when you were telling us about this adding of links here, this reminded me a little bit, but it's different from how people create small world networks, where you would take one of the short links and eliminate it and make it a long one instead. So by doing this, you would lose some of the short ones, but you would also get long ones. Do you also get different low energy physics in this case or not? Or how?
Basically, okay. For some reason, the network and the graph theory people don't like don't talk about the spectral dimension so much. I think the reason is that there are no way to do it exactly. They talk a lot about the first eigenvalue, what is the first eigenvalues, but they don't talk about the density of states. Yet, any small world network that I know and that I have asked to people doing graph theory as a gap spectrum. This one is not a small world network, and as I said, for me the most interesting regime is the weak long range, where you still have a finite density of space, but you can control it via sigma. And this graph can do that, and I don't know any small world network that has a continuous spectrum. This is also tunable, but in general, all the small world networks that I know, they are gapped, or they have a finite spectral dimension, and as soon as you turn some parameter, they immediately become gapped. So tunability I have seen only in this model here.
Yeah, thanks a lot. So as far as I understood, that your argumentation relies a lot on the low energy part of the spectrum. So what about if you consider non-equilibrium dynamics? So for example, can you show that Lieb-Robinson bounds are faster than linear? And I
think Lieb-Robinson bound will, since it's something that pertains long times somehow, it naturally probes low energy, because long times you need to have guys that are infinitely extended to go there. You can do the Lieb-Robinson. I am not expert on Lieb-Robinson, of course, but I guess it's pretty safe to assume that when you do Lieb-Robinson bound on a quadratic model of quasi-particle with dispersion, you will get that the cone is bent, and it bends and it bends and it bends. So this, I think, it's safe to say. So this guy has a nonlinear light cone. Whether it's exactly the same of long-range interacting, I cannot answer. There are other experts that can.
Okay, that makes sense. Thanks.
Any more? Okay.
Nicolo, can you relate the comment you made about the scaling of the smallest eigenvalue to the centrality of a network? In the centrality, which is the largest eigenvalue of the adjacency matrix?
You know, I really tried to do that. Okay, no, first of all, you can show, so basically, let's remain in the regime alpha larger than D. You can show that the smallest eigenvalue of the network, that the gap closes, so it approaches the zero with a scaling exponent that is 2 over the spectral dimension. So of course, the closing of gaps and it's related to the spectral properties. I tried hard to connect other measures that people in network theory use, like mean degree distribution. I failed. As I said, I can just notice that all the networks that are small world, so that they have a degree distribution, whatever, power law, they have a gap spectrum. And so for what pertains to long-range interacting community, they are in the alpha smaller than D world. This is the only thing that I noticed. I tried, I asked everyone, so can you connect the fractal dimension? And the answer is, well, there are inequalities, this is not proven, this may be true, we don't know.
And for non-Hermitian systems, do you see the gap in the complex plane?
Yes, of course.
Yeah, okay.
Yes, I was trying to imagine what you said about the cone. So I guess that you need the averaging, right? Because a specific realization of this network would be kind of short-ranged. So I have a linear cone for several steps, and then it would jump somewhere, right? And so it's just the average that would give you the curvature.
But basically, I think that the average feature are, so in the sense, this structure is self-averaging, that there is no frustration. Obviously, that's so. In the thermodynamic limit, you don't need to make any average. This is just one structure. So when you talk of Lieb-Robinson bound, normally you talk in infinitely extended system, and it will be band light cone. How do this intertwines with a finite system? This I cannot say, but this question that you asked, it would be the same for long-range interacting system. So a long-range interacting system with finite sides is just a sum of cosine. The spectrum is analytic. Then there is no there is no bending of the light cone. So this always occurs in the thermodynamic limit, both for the long-range system and for this network, because the thermodynamic limit here automatically averages, because you realize different disordered configuration in different locations. Then maybe a question, how fast this averaging goes, this I cannot answer. It depends on the model.
Okay. If there are no urgent questions anymore, let's send Nicolo again.
Thank you, guys.